Hello and welcome to the second part of the two-part lesson on Add Local Sizing task of the Ansys Fluent Meshing Watertight Geometry workflow. Most of the CAD geometries used for simulation will have some combination of curved features, thin structures or narrow gaps that may need to be resolved accurately. For this, we have the curvature and proximity size control methods in the Add Local Sizing task, which will be the focus of this video. Sounds interesting, right? Let's get started. Launch Ansys Fluent in meshing mode and start a new watertight geometry workflow in Ansys Fluent Meshing. In the Import Geometry task, select the provided electronics box geometry file. This geometry consists of an enclosure around a PCB containing geometrically identical pairs of heat sinks and capacitors as shown here. Keep in mind that this is a representative geometry intended for instructional use only. Select Yes for Would you like to add local sizing under the Add Local Sizing task. Now, under the size control type, select Curvature. The curvature setting is used for refining the local sizing based on the underlying curve or surface curvature. You will notice that the additional settings are added to the task. The curvature sizing requires four main parameters to be defined: local min and max sizes, growth rate, and the curvature normal angle. The local min and max sizes allow us to specify the minimum and maximum sizes of the elements for the surface mesh respectively. Keep in mind that these sizes are measured tangential to the surface. The growth rate specifies the increase in element edge length with each succeeding layer. These settings prevent the mesh from becoming too fine or too coarse on the scoped surfaces. Let's select Walls Capacitor 2 and set the local min and max sizes to 0.3 and 1 respectively and keep the default value for growth rate. The main setting of this control type is the curvature normal angle. This angle is the maximum allowable angle between 0 and 180 degrees that one element edge is allowed to span for a particular curve. For example, a value of 10 would mean that a division will be made when the angle change along the curve is 10 degrees and therefore a 180 degree arc will be divided into approximately 18 segments. In this way, we can limit the number of elements that are generated along a curve or a curved surface if the minimum size is too small for that curve. Keep in mind that the default value of 18 degrees is sufficient and works for most of the cases. Smaller values are recommended to be used in cases where the underlying geometry is highly curved, such as the leading edge or trailing edge of wings. For this demo, we will enter 10 for curvature normal angle. Lastly, we need to define the scope of this localized size control in the Scope 2 field. We can localize the size control to faces, edges, faces and edges, or edge labels. Let's set the scope to faces and click on Add Local Sizing. You can see that the curvature local sizing task is added to the workflow. Now let's create another local sizing for the Walls Capacitor 1. We will keep the same local min and max sizes as before. However, let's change the curvature normal angle to 20 for this one and click on Add Local Sizing. Now since both the curvature sizing have been defined, we will move to proximity sizing and make the comparison later in this lesson. Proximity size control type is used for refining the mesh by specifying the number of cells to be used to resolve gaps either between edges or faces. In the Add Local Sizing task, select Yes. Now under Size Control Type, select Proximity. You will notice that additional settings are added to the task. the proximity sizing requires 4 main parameters to be defined: mean and max sizes, growth rate, and the cells per gap. The local mean and max sizes are measured between the proximity boundaries. The growth rate specifies the increase in element edge length with each succeeding layer. These settings prevent the mesh from becoming too fine or too coarse on the scoped surfaces. Let's select Walls Heatsink 1 and set the local min and max sizes to 0.3 and 1 respectively and keep the default value for growth rate. The main parameter for this control type is the cells per gap setting. This setting allows us to set a minimum number of layers of elements to be generated in the gaps. These gaps are defined in either of two ways: the area between two opposing boundary edges of a face or the internal volumetric region between two faces. Set the cells per gap to 4. After that, we need to define the scope of this localized size control in the Scope 2 field. The option Faces and Edges on Proximity can be used when the prescribed number of cells across the gap need to be respected on all transverse sections of proximity walls. Let's set the Scope to Faces, leave the Refine Thin Regions option to default and click on Add Local Sizing. You can see that the Proximity Local Sizing task is added to the workflow. Create a similar local sizing for Walls Heatsink 2, but set the cells per gap to 2 to see the impact of this parameter. Now let's see the effect of these local sizing on the surface mesh. We will keep the defaults for the Generate the Surface Mesh task as we want to focus on local sizing in this lesson. Click on Generate the Surface Mesh and Ansys Fluent Meshing will create the surface mesh based on these settings. Let's look at the generated surface mesh to see the effect of these local sizing. We will begin with curvature local sizing. For that, first let's hide the enclosure, the inlet and the outlet surface and zoom into the capacitors to see the effect of curvature normal angle. For the capacitor on the left, a value of 10 degrees is used and as a result, we get approximately 36 mesh nodes around the circumference of the circle. On the other hand, for the cylinder on the right, a value of 20 results in approximately half as many elements along the circumference. In case of proximity local sizing, the impact of the proximity size control, specifically the cell per gap parameter, is clear when looking at the mesh for the two heat sinks. The surface mesh for the heat sink with cells per gap of 2 has less elements across the gaps as compared to the heat sink with cells per gap of 4. Let's now compare the impact of scoping method on the proximity local sizing. Both the heat sinks have same local sizing settings except for the scoping as shown. One heat sink has been given face scoping while other has been given edge scoping. You can clearly see the effect of scoping the local sizing to edges compared to faces by comparing the surface meshes on the two heat sinks. The local sizing is applied only at the edge of the face and the size of the elements increases while moving away from the edge where the sizing is being applied. This brings us to the end of the lesson. Let's summarize what we have learned in this lesson. We understood what curvature local sizing is and how to implement it. Then we learned about the proximity local sizing and its application. Finally, we compared the effect of edge and face scoping methods on proximity size control method available in the Add Local Sizing task of the Ansys Fluent Meshing Watertight Geometry workflow. With that, let's wrap up the lesson.